All right. Yeah. All right, so we are recording now. All right. Thanks everybody for coming. We're going to get started. Looks like we've maxed out our physical and online attendance capacity, which is awesome. Good job, Jim.
I gave up my spot, so now
Okay.
we can't see questions.
Okay.
Hopefully they pop up.
Okay.
Yeah. So please keep an eye on questions. So today we have Jim Thorson, who hardly needs an introduction, but I will do one anyway. He is presenting, 3 papers in one talk today? Yeah, awesome. So quick intro, especially for our visiting prospective students. Jim did his bachelor's in environmental studies and philosophy with a minor in econ from Emory University. A master's in the Department of Fisheries and Wildlife at Virginia Tech, and did his PhD here at SAFS with the Punt Lab in 2011, correct? Yeah, nice. And was then a postdoc with NIMFS, and is now working for the National Marine Fisheries Service, currently at the Alaska Center. What's your official job title now?
So I'm program lead of the Habitat and Ecosystem Process Research Program.
Nice. Yeah. Well, thank you. So Jim does ecologically motivated research, and statistically innovative that has direct bearing on natural resource management. Some of these research themes broadly include some meta-analysis testing, predictions from ecological theory, a lot of spatiotemporal modeling, which is a lot of what we'll get into today, I think, and estimation of biological processes varying over space and time, and development of testing of new ecological methods. So with that, let's welcome Jim. Thank you for coming today.
Yeah, thank you. Yeah, thanks everyone. So I'm really excited to be here. I always try to give one of these a year, and it's often my favorite talk of the year. It's a lot of fun to have a chance to continue the connection with UW. As was mentioned, I'm the program lead for Habitat and Ecosystem Process Research Program at the Alaska Center. And so I'm in charge of trying to facilitate cross-divisional research at one of the biggest fishery science organizations in the world. It has 315 FTEs at this point across several different centers. And, the idea is to help stitch together these different programs with kind of cross-cutting research. So I kind of feel like my job in part is kind of spinning up zany, weird research topics, and I'm excited to continue trying to do that with students. Today, I'm talking about progress we've made in the last year in developing advances for spatiotemporal modeling using this R package FAST for vector autoregressive spatiotemporal models. And I'm trying to do one of these each year to kind of help orient what are the new developments in that. And that's the intent of this talk. I think I'm going to get a pop-up window every time somebody tries to join and can't. So I'm sorry in advance. Let's see. This actually might make it hard to, here we go. So I'm trying to get used to using the new PowerPoint formats. Ugly, and then I'll just go back to randomly finding pictures. I don't have time to customize these pictures, but I was realizing that a seal eating a salmon brain is a bit how it feels sometimes when I'm actually working on this code. So it seemed appropriate. So first, I'll try to summarize a little bit about the spatiotemporal modeling package FAST that me and others have been developing, testing, and demonstrating. Oh man. So next. Yeah. So in a paper that came out this last year, we've got a series of guidelines showing how to use it for different purposes. And the reason I think that spatiotemporal models have a big prospect for growth is that they, I claim that they kind of can unify a lot of disparate activities that go on within NIMFS and other regulatory agencies. So, we have statutory authority to do reporting to different stakeholders at different time scales and spatial scales about stock assessment, so regulating fishing, habitat assessment or designating sensitive habitats for deep sea corals and others. Integrated ecosystem assessments for looking at kind of regional drivers of ecosystem dynamics, and climate assessment, for engaging with the IPCC globally, or Pisces ice for regional downscaled climate forecasts. And all of these are, it's a big portfolio of things we try to do, but all of them can be answered through, I think, this toolbox of spatiotemporal models that basically treat as variables localized density, how it varies over time, and how it compares across different species. So these multivariate spatiotemporal models can be fitted, and then you back out different variables that refer to what you're interested in. And the benefit of that, I think, is that you can include biological localized mechanisms are, often what we think of ecologically and can test experimentally. We can improve communication by doing downscaled models. And by sharing these sort of same methods, we can hopefully share development costs, review standards and burdens of proof. So in this paper, I'm just going to quickly go through this 2019 paper. There's sort of 3 case studies we looked at. One is sort of the stock assessment picture of what we might want to know. So if you fit a model, spatiotemporal model, in this case, the arrowtooth flounder, you get, if you don't know a system, you get kind of a broad scale story of what's happening. You can get an index of abundance, the bottom left, like you might fit a population model to. In the top right, you can get a measure of effective area occupied, and that's increasing over time, representing the spill of this species from offshore inshore in the eastern Bering Sea over time. And you can get this northward center of gravity. This is a statistic representing movement poleward as it does that spill. That's something that Malin, Pinsky, and others have been tracking as sort of a measure of spatial ecology. So instead of just the index of abundance that stock assessments looked at for a long time, you can get this kind of richer picture of single species spatial ecology. Alternatively, you can do what's called ordination. Somebody was just telling me that James Clark and Urban have sort of arguments about how to do multivariate statistics, and if anybody's done that in Julian's class or elsewhere, like Urban might do NMDS for stuff, and you get these kind of nonsensical sort of uninterpretable plots. Whereas I think, James Clark kind of talks about actually ordinating with a model-based ordination. And you can do that with a spatiotemporal model where every species, in this case, there's 8 species in the Gulf of Alaska. Each of them has a certain association with a spatial factor that's estimated as a Gaussian Markov random field. So this first factor is, has high density around Kodiak and is associated with species 6, 1, 3, and 5. So flathead sole, walleye pollock, Pacific cod. Pacific cod's the only one I've looked at recently, and I know they have hotspots near Kodiak. So, so there's sort of one complex based on a spatial niche that's, ordinated by that first factor. There's another factor that's approximately orthogonal. You can do the same thing with the spatiotemporal variation. So 84, 93, 2001, 2009, 2017. You can look at how, interannual variation ordinates, where in this case, I guess everything, like 1, 7, 6, 4, 8, 3 are all positively loaded on factor 1. And then factor 2 is associated with a different set of species and their interannual dynamics. So this is a way of compressing community dynamics down to sort of this like classic urban style ordination. So that's sort of community analysis, integrated ecosystem analysis topics. Or you can do kind of climate forecasts. So in this case, this is the proportion of biomass for 5 different species in the California current, the proportion of biomass in California, Oregon, and Washington waters. So you can fit a model, a multivariate model, and then post-stratify results to see what how much is associated with different ports, and then forecast that forward. It's only fitted to data through 2015, and then 2016, 2017 are forecasts. And so there's this delay in fisheries management where we fit a model to a certain year, and then we have to regulate fishing for several years after that. And the claim is that if we can link climate forecasts to our short-term forecasting, we could do kind of climate-ready fisheries management. In this case, there's species like lingcod that have been differentially recovering in the northern and southern California current. And if we could do a climate-linked model for that, we could do more kind of proactive management of fishing opportunities. So that's sort of a climate forecast example. So this this is sort of the scope that we're trying to work with. There's sort of 15 decisions that we laid out for how to do this. You know, one of them is like, do a model at the spatial scale you care about, integrate different data. These are all kind of common sense, but I don't think anybody had laid them out. So for the sake of time, I'll skip through most of that. But hopefully that sets the stage for why this is sort of a tool that I'm trying to help people develop and test and demonstrate. So today I want to talk about 3 other talks for where I think we can use this based on new developments. So one of them, the first is with co-authors Kirsten Holzman and Grant. Grant's here. Thanks for coming, Grant. Yeah, so randomly assigned larval fish. And it's a spatiotemporal model of intermediate complexity. So Ava Plagiani has made a lot of hay talking about these mice models. And has like kind of cute graphics. Actually, Gavin Fay instructed me to bring up something from, you remember, you were on that email. What did he talk about? It doesn't matter. It was some Muppet thing. Yeah, so I'm hoping to use like cuter graphics for mice and space models. And I think that it's a way to kind of have these sort of statistically fitted small multi-species models that you can use for tactical fisheries management of ecosystem interactions. Yeah, so the question, how do we explore ecosystem dynamics for spatial management? And the approach is to extend this vast package to include fishing mortality, species interactions, and use it to estimate biological reference points, these targets that we use to manage fish. So the context is that a couple years ago I worked with Doug Swain and Steve Munch to publish a paper on, well, it was a MIST package that had vector interactions. So this is a vector autoregressive state space model. And it estimates this matrix B that's the community matrix. So Tony Ives has written about this and Brian Dennis, how B is essentially the first order Taylor series expansion of a general nonlinear model. And that B matrix represents a lot of things about stability of the ecosystem. Yeah, so it's this B matrix in log space of density D plus omega, which is a spatial variation, and epsilon, that's a spatiotemporal variation subscripted with S for space and T for time. And, you know, people talk a lot about species modules. So there's kind of, you know, ecosystems are probably made up of tightly interacting species that are weakly interacting amongst them. And so that B matrix has a certain structure that you can estimate to get at this kind of stability of the ecosystem. And so the way we extend this to VAST is we use this Poisson-linked delta model that I'll talk about. We include spatial and spatiotemporal variation. We include the same mechanics for covariation among species. Like a factor model. We include fishing mortality that you have to input as data for now. And then you back out unfished biomass, what biomass would occur in the absence of fishing. And you can also back out the fishing mortality that would result on average in 40% of B0, which is an SPR target of 40%. So those are biological reference points you can back out with that structure. To get into the equations a little bit, it's a model that's defined in terms of 2 linear predictors. This is the Poisson-linked delta model. So one of them is numbers density, N, at every location S and time T for category C, species C. And the other one is log biomass per individual. The product of biomass per individual and numbers is biomass, total biomass. So it's a way of expressing population density in terms of these 2 variables that have sort of biological meaning. You fit the delta, this is sort of a standard delta model with an encounter probability and a biomass per encounter. And you just do some algebra to solve for how to convert numbers to encounter probability using the C-log-log link, which Fisher originally developed. So I published that last year. And then the standard vector autoregressive model, well, if you do a first order Taylor series expansion of dynamics around interactions and around fishing mortality, you get a function that looks like this. So B, again, is this sort of linear approximation to the nonlinear dynamics. And F is the fishing mortality rate. It's in log, so it's additive. And if you restate that as a spatiotemporal model, we add an omega and epsilon, the kind of persistent spatial variation that we ordinated in that second case study in spatiotemporal variation. And then the trick that I guess I hadn't worked through before is to how to do that in this Poisson-linked delta model. So essentially fishing mortality that you put in, you pre-specify propagates over time following this sort of first order process. So B, if you have a press experiment in these sort of linear models, it converges exponentially to its long-term equilibrium. And that's what this B to the delta is signifying. And then this squiggly represents the proportion to which fishing is affecting numbers density versus biomass. So is fishing down causing you to encounter them less, or is it causing you to have lower biomass when you encounter them? So we could, anyway, so this is how you express it in this Poisson-linked delta model. And then and then it's there in VAF. So I can fit it to, we can fit it to data for 4 different species in the Gulf of Alaska, using fishing mortality rates that are shown for each of them from 82 to 2015. The dashed line is the fishing mortality that we hardwire in. And if we can fit a model, an index standardization model that has no temporal structure, no interactions in identical species that has density dependence, or no interactions in heterogeneous density dependence among species, or a model with species interactions. And if we use AIC to select models, we find that the one with interactions fits the best. So that's sort of like the victory for ecosystem science, that there is signal of species interactions in a data set like this. If you compare all of them, though, they all give you pretty similar estimates of biomass trends over time. So for index standardization, maybe not that important. The point, though, is that you can then use that relationship to back out what's unfished population density across space. And so that's shown at the top for each species. And you can also estimate what's the density, biomass density across time. So, for instance, I guess, do we know anybody like Pollock? What was going on with Pollock and Goa in 2005?
Looks good. I go with the ROTs being high in 2005 and down.
Okay. You mean like that's, that happened, or?
Yeah.
Okay. Well, hopefully.
Vice versa for Pollock.
Okay. Yeah, so I mean, the point is, it shouldn't tell you anything you can't see in the data, but it's a way of assembling the data in a way that you can visualize more broadly, you can estimate species interactions, and you can downscale spatial protections. You can also back out that SPR target and the unfished biomass and plot those for the different models. And if you add interactions, you get much broader BRPs, which kind of makes sense. Those interactions are hard to estimate, and so you get probably a more realistic picture of how uncertain we are about how the targets we want to hit. And it's more, it adds more variability for fishing mortality targets than biomass targets. And then you can plot it as a stock status plot. You can plot biomass and fishing mortality relative to those targets and get this, which we typically use to manage stocks. We try to get stocks to be less fishing than the F target and more biomass than the biomass target, unless you're Ray, and then you fluctuate evenly between them.
Any interactions with the that are relating to trophic interactions, or is it just the species interaction based on data?
Yeah, it's just species interaction. You could hardwire the interaction matrix, and I think that that's a future direction I'd want to go. So this has been really slow because we asked Karam to do an internal review, and he was smart enough to realize that some of the interactions were not the direction we expected. I don't think they were horrible, but so I think if we were going to use this for something, we'd probably want to hardwire the interactions. But yeah,
is that matrix parameterized somehow, or do you estimate the elements individually?
Yeah, you estimate the individual elements, and then there's kind of a neat, like in the Steve Munch and Doug Swain, we kind of came up with a couple parsimonious alternatives to estimating every interaction. So the kind of rank reduced versions of it.
It went kind of quick, but you said that you used a linear predictor of a nonlinear, presumably nonlinear.
Yeah, dynamics.
How do you think that would impact this?
Yeah, so I like doing it for Alaska because, like if you do a linear approximation of dynamics, it's perfect asymptotically as you zoom in, and it gets worse the further away you get. And so, Alaska, where we've never really overfished that hard, I'm hoping that a linear approximation is reasonable. Yeah. And then, you know, doing a simulate.
Wouldn't it be better if you had explored more of the phase space of?
Well, because it's so stiff in terms of the, you'd probably get more precision if you explored more, but the approximation would be worse. So there's probably some trade-off there. Yeah, of course.
I'm curious, and we can talk about this later, but the lower right, that's halibut.
I hope so.
And so what, can you talk about like what your models say about halibut relative to?
Well, I don't know what anybody else says about halibut, so I assume this is right. And what is happening to halibut in Lagoa?
Well, I mean, I'm just looking at, it's just in the Gulf.
Yeah.
So that's interesting. And then, so on the x-axis, it looks like they're about at their average unfished level.
Yeah, and
all of those years.
yeah, and it's the estimate for that arises from the fact that fishing mortality rates are pretty low, essentially. So I took the fishing mortality rates out of the most recent stock assessment, and I'd say that's the other big problem with this approach is you have to hardwire F.
Coast-wide and linear.
Yeah, totally right. Well, I forget how I got that out of the.
We can talk later.
Yeah, let's talk later.
Yeah.
So clearly there's sort of, well, I'll come back. And then if you fit the data, if you fit the model with 4 species and then you simulate data at a higher spatial resolution, you can simulate dynamics that look like this. Like it's like a self-test simulator. And then if you fit the data but exclude all but 2 of the 4 species and you fit it at a coarser spatial resolution, it's sort of supposed to be like what happens if you're missing a piece of the ecosystem and you're missing some of the spatial resolution. You get back in one simulation replicate, you can get back something that looks like this. So the idea being that at least in simulation land, you can get back some of the kind of right spatial patterns for unfished biomass or for density in 2015 in the bottom. And if you do that for just picking out 2 of the 4 species, the true estimate, the original estimate that you're using to simulate data is shown in the dashed vertical line. And then the simulation distribution is shown in the histogram, and the idea being that you can get something that's approximately unbiased, even if you're missing pieces of the ecosystem. So I don't know how general that is, but it's just a self-test with kind of mild misspecification seemed like a beginning of how to explore the kind of capabilities of this. So this is the end of this first piece. Like a lot of these, I'd be excited to talk more. And, my personal opinion is usually that different models are good for different things, and it's our job to figure out when we trust them for a different purpose. So I certainly don't claim that this should replace the halibut model.
Nobody is just.
Totally, yeah.
But are the Fs applied kind of consistently with the spatial biomass? Is that how that works? Because presumably you didn't take F by each.
Totally, yeah.
Spatially.
No, exactly. So the F is constant across space, and one thing if there was some interest in doing something like this, like for instance, in my role as like head of the EFH program, I think that if we're going to do level 4 maps of productivity for EFH, then we end up needing to have some spatial maps of fishing effort or removals. And like maybe we get that from Brad Harris at Pacific, somewhere in Alaska. Alaska Pacific University, that's the one. Yeah.
I'm just gonna check go-to meeting real quick.
Okay.
Sorry.
I'll just. Any other questions from?
Okay, good. Cut out for a sec, but we're good.
Okay, perfect. So that was the first one. Is this like now up here?
Just click the PowerPoint, it should go away.
Okay. Okay, so the next piece was how to think about this for oceanography. And this is sort of a trick that, essentially this is sort of a trick that Mark Sherrill has known about for a long time. So Mark's a really smart guy. He's been exploring all these different models, not in a spatial way, and it's been a lot of fun kind of trying to connect the, expand that into kind of spatial temporal models. This I understand to be a picture of Lake Alignagik, but that's all I know because Ray never flew me out. Yeah, I know, it's true. Now I can't accept any money. So, yeah. So the question is, how do you identify kind of annual variability from multivariate, noisy, zero inflated biological data? So physical oceanographers going back to the 60s and 70s, started getting these like weather balloons or something and these measurements of temperature and precipitation, and they started doing, like on punch cards, they started doing factor analysis using algebra, and they'd quantify it as what they called EOF, so empirical orthogonal functions. And if you've ever heard about the El Nino Southern Oscillation, the ENSO, that's an EOF of climate measurements, or the Pacific Decadal Oscillation, PDO, that's an EOF. A lot of what we know about physical oceanography is kind of these descriptions, these sort of statistical descriptions of average patterns of covariation spatially and how they assigning years some pattern on that axis. And so I was kind of curious to see if you could do this with a spatiotemporal model, but fit it directly to biological data, because I want to see, well, essentially Mike Litzow, sorry, I should have pointed out, Lorenzo Cianelli is down at OSU, and Mike Litzow is at University of Alaska Fairbanks in Kodiak, I think. And Mike has a recent paper in Proceedings of the Royal Statistical Society that points out that the PDO that Nate Mantua originally showed is associated with salmon returns, that relationship weakens after this 1989 regime shift, when the relationship between regional PDO and local environmental conditions seem to change. And so there's this sort of big, like God has this big structural model in mind where there's like something physical affects something else and affects something else and then affects biology. But all those relationships are kind of time varying and climate's messing it all up. And so instead of trying to map out all of those processes, I guess I was curious if you could just analyze biology, get the kind of physical drivers from that, and then go run with that and never talk about a mooring again. And so the approach is to use this multivariate extension to EOF, apply it to biological data, invert the indexing of years and species, and basically say, is this species positively or negatively associated with, is this year positively or negatively associated with a certain spatial pattern? And so to kind of lay this out a little more, the PDO is shown, I mean, this was pulled off the internet, so I'm sure it's right, that the warm phase has this kind of cold portion in the North Pacific, and the cool phase has this warm portion in the North Pacific. And the PDO looks like this, there's a monthly value, and people will take this and plug it into their chosen biological model to see if it's correlated with salmon returns or rockfish or whatever, Similarly, Di Lorenzo, who I don't, you know where he is?
Georgia. Somewhere.
Georgia? Okay. Probably not listening, so apologies for your name, Dee. That's a joke. So NPGO is supposed to be an orthogonal function. It has a different temporal trend and is associated with different patterns. And Mike Litzow has been claiming that the NPGO is more associated with salmon returns. At CJFAST, we get all these papers constantly arguing about whether PDO or NPGO is driving this, which they stopped assigning to me. And so first I want to show that we can back out these two patterns with VAST. And the way to do this, the way the structure of an EOF in a structural model is that you've got a linear predictor with a link function, some intercepts. This is the index. This is the index phase. This is the index map, the product, and the sum across multiple ones of those indices is the linear predictor. It's the net effect of all these indices. And then you associate that linear predictor with some data via some function, some PDF H. And so if you do that, and fit that to temperature that Mike pulled off the internet. The first index, well, normally they mean center every location, so they drop this first variable, but as expected, if you do this for sea surface temperature, the main prediction is persistent spatial differences. The second one, you get a correlation of 0.92 with the published PDO, and you get this map that shows that positive phase of the PDO has this kind of cool water in the Central Pacific and warm water inshore, and that sort of has something to do with weather where we are. And then the NPGO has a weaker correlation for reasons I haven't really dug into, but it's correlated. So there's something different about how they're doing the second index that I haven't tracked down. But in general, hopefully you're willing to buy that you can back out the same signal as the PDO. And if you compare the spatial areas associated with it, again, we're getting the same estimate of cold water in the Central Pacific associated with the positive phase of the PDO. And then the positive phase, the NPGO, is associated with this sort of cooler waters in the California Current and warmer waters in the BC and Goa. So it makes sense that maybe this is associated with some difference between Alaskan and Pacific salmon to me. And then if you fit that same model to 12 bottom associated fish and crab species in the eastern Bering Sea using the same Poisson-linked delta model, the first index again is persistent spatial variation, which we'll talk about. The second one is this kind of multi-decadal trends in some component of the biology of the EBS. And the third one is this more interannual variability, and we'll come back to that one in a bit. So it kind of breaks down as kind of persistent, long-term, and short-term, kind of like how the PDO and NPGO do. If you actually look at the maps associated with these different indices, well, the first one, factor 1, just ends up estimating kind of the spatial niche of each of these species, the kind of long-term distribution. The second one is associated most strongly with flatfishes and essentially represents this sort of multi-decadal thing that's happening with flatfishes in the eastern Bering Sea, where, for instance, northern rock sole, I guess, is decreasing in abundance in the north. Arrow-toothed flounder is
columns?
what are they up there?
No.
Oh, this is factor 2. This is factor 1, factor 2, factor 3. So the same order is on the left-hand side. I just broke it up to fit on the slide. I guess arrow-toothed flounder, over time, the relative density is decreasing offshore and increasing inshore, which we know to be the case with arrow-tooth. And then the third one is the most interesting. I'll actually just skip to the punchline. The third one is most correlated. It's highly correlated with sea ice extent. So, BZRP was I think a $40 million program between NOAA and NSF that concluded that sea ice is a major driver. The sea ice extent and how it sets up the cold pool is the major driver of plankton blooms and is driving distribution of species in the EBS. If we just call that third one, it's 0.75 correlated with cold pool extent. If we call that cold pool extent, we see that, in years with high cold pool, we get decreased density of pollock and cod in the north. 2018, which this didn't fit, was when it had the lowest sea ice extent and also this sort of erroneous, unusual distribution northward. So this is sort of predictive of what happened in 2017, 2018. But I haven't really heard people talk about the cold pool effect on arrowtooth or tanner crab, snow crab. You get kind of counterintuitive results where, I guess in the high sea ice extent, you get decreased density of tanner crab in the north, whereas snow crab, it affects more the more further south.
Are these fit to biomass over the entire size spectrum of the species? Like
Correct.
All the little ones and all
Exactly. And as observed by the nymphs 83112 gear. So this is sort of a synoptic summary of I think of the cold pool. You can back out from, unlike EOF, it's easy to back out the predicted density for each species, so you can kind of reassemble all of it together. I mean, this is what David Wharton says is the benefit of multivariate, model-based multivariate analysis, that you can see what you end up seeing. So arrow-tooth flounder, we kind of regenerate this sort of spill inshore, offshore, inshore, sorry. And tanner crab, I guess, is going down in density in the south over time.
These are predictions?
These are these predictions for, and Pollock was doing horrible when Jim lost his hair and came back a bit. Yeah, sorry, I didn't. It's beautiful. Yeah, and then, yeah, so okay, so the point being that in the future, I'd love to do these EOF jointly with physics and biology, and then estimate the kind of cross correlations, the kind of mechanics you can build with a ROMS model, but I think you can also estimate statistically if you have, dense enough sampling, and I'm excited about doing that. I think you can also build these models as a data integrated model to maximize the covariance with other processes. You could just take this model and plop a salmon smolt to adult return model on top of it and figure out what's the spatial map most associated with positive returns for Chinook, in the Columbia River. And then the final one is, which I am doing in a paper that I'm presenting at the wildlife seminar in June, is building the spatially varying effect of cold pool extent for individual species that we can use during index standardization. So how do we use cold pool extent to figure out what's happening in the northern Bering Sea that we didn't sample in 2015, 2016? So, so that's sort of the end of that piece. Any questions for now? I think I've hit the kind of like shock and awe portion, so perfect. And then the final piece was just trying to confirm that this is useful for index standardization. So working with Stan and Jimmy and Ellie in the run up to the SAFE report, the stock assessment for Pollock. I should just put on my Jim hat and say that we catch more pollock than all of the country of Australia catches fish, and it's better looking than any fish in Europe, and whatever else you say. But so it's an important stock to figure out how to estimate what's happening, and I'm excited to have Cecilia O'Leary working with us here at UW going forward. So thank you, Cecilia, for coming to join us. So what we're interested in is we've got this bottom trawl footprint from 1982 to 2018, where at the beginning, back in 82, I guess we had enough money in 82, 85, 88, and 91 to do resource surveys up in what we now call the northern Bering Sea, so past the St. Lawrence Island and the Norton Sound. But I guess we didn't find enough fish that we thought that there was any fishery up there. We actually declared this whole area in the northern Bering Sea the Northern Bering Sea Research Area is what's it called, anybody? And we closed it to fishing pending more information. Bottom trawling pending more information. My predecessor in HEPR, Mike Sigler, in 2010 worked with people, Phyllis Stabenow, Jeff Knapp, to get funding for a survey again in 2010. They again didn't see very much. And we went back under the Loss of Sea Ice program in 2017, and we found almost a third of all pollock and almost a third of all cod had suddenly just showed up in this portion that we considered outside the stock boundaries. So, if does anybody know Ben Fissel's value of pollock number offhand? Like dockside. $500 million. So if a third of it moved up there, that's like $200 million worth of potential cash that moved out of the area we typically think of as the footprint of that fishery. Even more moved up from cod. People freaked out. We got emergency funding approved for this kind of emergency survey in the northern Bering Sea in 2018, and we're doing it again in 2019. And it's probably the biggest, I would say it's one of the biggest stress points on fisheries management nationwide is this kind of climate-driven shift northward. It's the only case I can think of the biggest consumers of an ecosystem, broad scale, invading a new ecosystem in land or on water. And so I think it's a fascinating ecological experiment that we get to witness, but also crazy to manage. So we're trying to figure out how we manage this. And one way is to try to fit a model to density for both regions while extrapolating density in years that we don't have any samples. And because reasons, I think that might be the best we can do historically, although Jim can comment. So we fit an index standardization model, but we change it by putting an AR1 process on spatial temporal variability. And we then post hoc stratify it to compute biomass in the eastern Bering Sea or the northern Bering Sea or both. And Holloway wanted to make sure that we did one with or without the localized effect of bottom temperature. So we did a model with bottom temperature, without bottom temperature, and got, absent differences in scaling, pretty similar results, although I can come back to that. But if you plot the total biomass, you confirm that, well, first of all, this is 2015, 17 and 18. 2016 has a huge confidence interval relative to the other years because a significant portion was likely to be in the north, but we didn't have a survey there. And so this loss in precision is the cost of not doing an annual survey in an area where you think a big portion of your population is. So you can already see that headline result is if your population's moving out of your area, you might as well get a few samples up there because you can probably buy a lot of precision cheaply that way. We're not as worried as maybe we'd have to be if it hadn't been at historical peaks right before this happened. But the proportion that's in the northern Bering Sea compared with the eastern Bering Sea, went up considerably.
Is that the one with temperature?
I think this was without temperature. If you look at effective area occupied, the effective area occupied expanded. Essentially, they had access to a broader range of the shelf, seemingly, and they moved northward and significantly northward and a little bit eastward. So these are statistics of spatial ecology. And then finally, if you compute these results fitting to an age stratified model, so a multivariate model that's fitting to each age, you can back out the age comps in each year from that joint model as well. So this is sort of like age comps that could go into a model just to show that we can do all of the kind of index standardization expansion that you want to do for stock assessment while combining data from multiple surveys. So with or without temperature, we get this sort of 80% being in the northern Bering Sea estimate in recent years. And the fact that it went from like 2% to 80% over the course of 5 years is frightening. Yeah, so I think that's it. But so I should have had a conclusion. But I guess the conclusion is that as I said in the abstract, I think that this is sort of it's a fertile ground for recasting a lot of old applied and fundamental questions in ecology in a way that we can make a lot of progress, especially when intercalibrating multiple years and multiple data sets. So I'm hoping that students and postdocs will continue to be interested in working with me to explore this stuff. Yeah, thanks.
I'm just going to see if there's questions up here.
Yeah.
We can do questions in here now, if anyone has any.
Yeah, Alan?
I'm wondering on that last section you had, at what point, and you didn't show any plots with uncertainty on them, did you?
Yeah, no spatial maps of uncertainty.
Right. At what point do you just say it's not useful to try to predict that year? So I'm thinking like 1982, you have one the closest observation is 2010, and you're predicting quite detailed spatial structure in 1982, which is when the survey didn't even get close to that real northern Bering Sea part anyways. So is there, do you look at uncertainty to decide these results are not very useful, but it seemed like it was giving you some predictions that.
There were data in the 80s if you go back to it.
So that's the first response. I get your larger point. In this particular case, we had those resource surveys in 82, 85, 88, and 91.
Okay, so there was some.
Yeah, but
oh, I see, yeah.
Peak confusion is like 2002, 2003, and depending, just to preface this June model I'll talk about, the spatially varying coefficient model. If you put in cold pool, somebody remind me, 2004, I guess, had a really small cold pool too. And so there's like somewhere right in here that particularly the model with or without this sort of spatially varying effect of cold pool has a hard time dealing with. And that's like right in here. So maybe it's like where it doesn't really matter that much anyway.
So is that a point where you might say these environmental covariance, temperature, whatever, are a benefit to the model?
Yeah, totally.
Trying to make a blanket statement across the whole thing.
Yeah, I mean, and like I've got a couple answers. One is that it wouldn't hurt for us to do more model ensembles, and you know, in my Hepper hat, you know, I want to support Chris Ruper's GlimGam RF package as a similar way of doing this stuff, and you know, it'd be nice to be able to do model comparisons the same way we do for assessment models. You know, in terms of when to do it, when to not do it, I think it all depends on what your backstop is. You know, like in this case, I think. You know, I think Grant Thompson went down this path of trying to fit a 2-area model and look at movement, and that was really hard to estimate, seemingly. And you know, so I don't know that that's the perfect way to do it. I think he just came back to a 1-box southern model for catch advice. Does anybody remember? And so, you know, like given that, especially for cod, they're actually fish, you know, long lining up there, I think. And so, you know, that would be a case where having some way of getting estimates for the NBS and EBS seems really important. You know, so I just think it's all about what your backstop is. You know, like the other case where we do this is with the basis survey, with it, you know, the ecosystem status report analyzes pelagic data for the northern Bering Sea and eastern Bering Sea, and they miss this, you know, one or the other in certain years. And in that case, you know, they could drop those years out. It doesn't cause much harm. And so it's probably worse for them to extrapolate wildly. And I've gotten a lot of pushback from ecofoci folk about trying to extrapolate in those cases. Yeah.
Have you been able to do anything to look at movement of stocks over the convention line in the Bering?
Oh, like into Russia? Is that what?
Density, yeah, over across the convention line into Russia.
Well, I'm glad you asked. We got a Russian, we've got a Russian national, Vladimir Kulik, who's showing up on Tuesday. And if you're interested, you should email me or somebody. He has a bunch of Russian survey data, but it's all in Cyrillic. So we're trying to figure out what to do with it. Cecilia is. Sorry, Cecilia. And we also did approve placing upward-facing acoustic moorings to build a wall to Russia. Just if you know, just to,
Underwater.
oh, underwater wall. Yeah, but we're not telling Trump's buddies. Yeah.
There's a question online from Charmaine about 2010.
Yeah. So 2010. You know, so the model has 2 ways of informing extrapolations into the north. One of them is temperature data. Well, it has a bunch of ways. One is temperature data. One is adjacency across years. So the 2017 high biomass is extrapolated back into 2016 with high variance. And then the other is extrapolation of adjacent spatial areas. And so anytime the stock has high density right up against the line, with NBS, it also kind of extrapolates that higher density out a little bit in a way that I think is, you know, its best guess. It has some statistical optimality conditions. So like 2003, 2004, I think maybe it's doing that a little bit. Data availability slide, sorry. Okay. So 2010, yeah, 2010 is when we did the first of these northern Bering Sea surveys that now we're doing in 2017, 2019.
These are all Mercator projections too, as well, right?
Yeah, totally.
Dramatic looking place.
Yeah, that's where you know I'm not actually a spatial ecologist. John.
Would it even be feasible to fit these data to something like a basin model where you're driving
Yeah.
driving the sort of movement and density by bottom temperature or something like that?
So Dana Hanselman and I, Anna Rindorf, and some other people had a paper in Proceedings of the Royal Statistical Society where we fitted area occupied versus abundance and showed that there's a significant effect, that it's higher in the eastern Bering Sea and for gadids. So that was 2016, and it estimated, I think, for EBS gadids, like for every 10% increase in abundance, there'd be a 2% increase in effective area occupied. Lorenzo Cianelli actually back in the day had a kind of another smart way to extend that, and that's that spatially varying coefficient model with density. So you could estimate a map that's you could say in a year with high density where do they go that they're not in low density. So he has an ecology paper in like 2007 or something about specific maps of density dependent, something more like Alex Basin model where it's implied not just that there's a relationship, but a specific area that they expand to. Yeah.
How do you define area occupied for just computing it from survey data set?
Yeah, so I spent a good bit of time thinking about, originally I did the kind of Mathieu Wallet way where you estimate a density function, you estimate the center of gravity and the inertia, he calls it, which is the variance of the density function. You can get a kernel on that and calculate the area of like a 75% quantile or something.
Oh.
And that's what I did originally. But that doesn't extend well to different spatial distributions. It's kind of an awkward way to do it, I think. And so now we do the effective area occupied is basically a calculation of total, how does this work? It's like total density, it's total biomass divided by average biomass. And if you do that in your head, you get units area, and it's essentially a measure of how much area is required to contain the population at average density. And that's nice because it's actually orthogonal. If you think of average density and effective area occupied, the product is total abundance. And so you can kind of break down spatial ecology into kind of two orthogonal variables.
But is it meaningful if you have a highly patchy distribution?
Yeah, well, all these models are working at a certain spatial resolution, but yeah, that one, unlike the Wallet kernel area measure, that one, it has the same properties if they're in separate boxes or in the same box, like separate patches, or the same patch, which is kind of why I like it now.
Any last questions? No? Let's thank Jim.
All right.